Good day, everyone, and welcome to another interesting session, which is part of an year-long series which the IEEE Electron Device Society Delhi chapter from New Delhi, India is organizing, along with our co-organizers, the Upadhyaya College, University of Delhi, and the National Academy of Sciences, India, Delhi chapter. Today we have with us Professor J.W.Swart from Brazil, and he'll be talking to us about his journey, his contributions to the area of transistors invention. So that's the 75 years of transistor, some Brazilian contributions, and 50 years experience in the field. He's a well-known figure in Electron Device Society and needs no introduction, formal introduction, but as in courtesy, and we do in all the talks. So he received his bachelor's and PhD of engineering in 1975 and 1981 respectively from the University of Sao Paulo, Brazil. And after his PhD, he worked at the following institutions: KUL Belgium, CTI Campinas, EP USP, SID Microelectronics, RTI US, and UNICAMP as a professor. Since his retirement in June 2013, he has been a collaborating professor at UNICAMP and served as director of the Center for Semiconductor Components at UNICAMP. He was the director of the CTI in Campinas and is a researcher level 1A by CNPq, is a member of the Academy of Sciences of the state of Sao Paulo, a member of the National Academy of Engineering, and is also an IEEE Life Fellow. He was president of the SB Micro twice, secretary of EDS, IEEE, and a member of the Board of Governors of EDS, IEEE for 2 terms of 6 years. In 2013, he founded the company J.W.Swart, Innovation in Semiconductors, and represented IMEC from Belgium until 2020. He is currently vice president of SB Micro and worked on CCD, NMOS, CMOS, and HBT process integration, device characterization and modeling, jittering process, plasma processes, rapid thermal processes, silicide formation and characterization, and IC design. His current research activities and interests include CMOS and MEMS devices, process integration, and IC design. With these words, I now invite Professor Swart to kindly share his screen to deliver his talk.
This was the title. I just started, and then this happened. So, and the aim of this talk is to offer a broad overview on semiconductor history, discuss some specific technological issues, share some of my own experience, and share information of some semiconductor work in Brazil. First, some words about my university. Is University of Campinas, or State University of Campinas, that is in the state of São Paulo. This is the map of São Paulo. And here, Campinas is just 100 kilometers from north of São Paulo. And this is a view of the university, this part all. And these are the buildings of electrical engineering. I hope you see my mouse, correct? Electrical engineering. UNICAMP is just some years older than 50 years old. We have 34,000 students, and the Faculty of Electrical and Computer Engineering is more close to 50 years old. And we have 600 graduate students and 700 undergraduates over the 5 years of the course. And it is one of the top electrical engineering schools in Brazil. So now let me go to the talk itself. Start in this outline: historical breakthroughs. First, microelectronics lab at the University of São Paulo. Then I have NMOS technology and ion implantation and read-only memory demonstration. Some words about my work on CCDs and gathering techniques, then active pixel sensor, silicides, integrated optoelectronics, structured IC design, and finally summary. I had to close my door. So just basic history is the invention or discovery of the transistor in December 1947, that are the 75 years ago that we are celebrating. You see the picture of Deen and Martijn showing the invention to Shockley, their boss. And just after that, Shockley developed the bipolar junction transistor theory and fabrication. And all the three got the Nobel Prize some years later. But something of this story you probably do not know. That is the story of Roberto Landel de Moura, end of the 19th century. He was a Brazilian scientist. He was also a priest, so in the spare time, he was a scientist. And he invented the transmitter of electromagnetic waves, light or RF, modulated by sound. And for applications like telegraph and cordless telephone. As devices, he invented a phonetic switch, a three-terminal lamp transmitter, and a selenium receiver. And he patented this in the USA some years from the year 3 patents in 1901 and the third one 1903. He stayed in the US to prove his invention through these 3 years. And you can find him in Wikipedia. So the principle was modulate emission of an arc lamp, or it could be other emitting device. The sound was used sound modulation by diagram connected to on-off switches with switches current through the emitter and as receiver a selenium resistor. He did a demonstration in São Paulo over 8 kilometers in 16 July 1889. And he had also a lab. He came to our city here, and where he stayed from 1892. So this was before Marconi, who did sample experiments, first experiments in 95, and first radiogram in 1900. But in 1905, when he came back from the US, he requested 2 chips from the president of Brazil to demonstrate communication and the use of it for sailing of chips to communicate between them. But unfortunately, some officers considered him lunatic, and then he quitted R&D. So that's kind of stories can happen in third world countries, very unfortunate for Brazil. Here is a picture from a book about him, it's in Portuguese. You see here this sound modulation device connected to switches, and this was the transmitter. But in just after that, we saw the invention of the triodes by Lee de Forest that gave rise to development of electronic circuits, and that was also very important later on for semiconductor integrated circuits. In 1958, we had the invention and demonstration of the first integrated circuit. The process, however, was very rudimentary, but the importance was the concept to integrate more than one transistor on the same substrate. And in the same time, at Fairchild, they invented the planar process for integrated, for fabrication of devices and integrated circuits. So the idea was on a surface, a silicon wafer that was oxidized, to do lithography and opening windows on the same plane, many of them. And that this principle is used until today for fabricating integrated circuits. So that gives rise to the integrated circuits, first for devices by Robert Noyce. Here, first example of this integrated circuit. And in 1960, the first MOSFET was demonstrated based on an idea that was 30 years old, but no one could demonstrate until then. In 70, we had the dynamic RAM by Intel, 1 kilobit. And I stress here it was on PMOS technology. Then the question why they started with PMOS and not NMOS once the electrons are faster than the holes. And the answer is because of the high positive effective interface charge at this interface between silicon and the SiO2. Being positive, it attracts electrons, which helps isolation for PMOS transistors, but would produce connection between NMOS in case of the P substrate for NMOS transistors. It would give rise to leakage between transistors. So that's the reason why the first they started with PMOS. Now some words about microelectronics. The first lab at the University of São Paulo, where I did my undergraduate and graduate studies. So first, I would like to mention that we had that started in 1968, and they demonstrated the first integrated circuits in 71 ECL gates. But this lab had a strong scientific support from Richard Anderson. We stayed there for a few years in that time and came back many others over the next decades. He was known by his pioneering work on heterojunctions with his Anderson rule model. He's life fellow of IEEE, but he passed away in 2 years ago, almost 2 years ago, and which was honored, described in memoriam in the EDS newsletters in July 2020. So now what work we did at this laboratory in São Paulo on NMOS, ion implantation, and read-only memory demonstration. Although industry was working with PMOS, here who became my advisor, Edgar Shari, he started with NMOS technology in the beginning of the 70s, defended his thesis in 74. And then in 74, I started to work with him, and my first task was to draw and help to design a read-only memory as undergraduate. And we designed a demonstrating chip of 512 NMOS read-only memory, and a few years later, a 2K-bit read-only memory. This is a picture of the 2K read-only memory. At that time, the masks were made sorry. In a very, very very manual way. Sorry. First drawing the layout on a paper by hand, then generate tables for each line, start and end point with codes, and then drawing this on a roulette file with a manual plotter with a knife to cut this. From that file, you make a first reduction print on a high resolution glass with some emulsion, and from that, with a reduction of 10 times or 20 times, depending on the machine, the settings, and then step and repeat with each die on another high resolution plate. And that was then the photomask for fabrication. Then, so that's how we made the memories and everything. Actually, this is the one of the mask of the memory. I think the metallization. We used ion implantation. Ion implantation using a homemade ion implanter developed by a colleague, Joel de Souza. And this was based on a patent also by Shockley. He patented the ion implantation accelerators in 1954, aiming to make short base bipolar transistors with retrograde doping to improve the gain of the transistors. But this technique turned out essential for MOS technology because it precisely controls the doping and is important for VT adjustment and other applications. So this is the homemade. Here is an extraction chamber. Here is a mass spectrometer, a second stage acceleration here. And so this could go up to 200 kV kilovolt acceleration. Then I worked on CCD and gathering techniques. CCD is also interesting. This was invented in 1970 by George Schmidt and Willard Boyle. Here you have the first demonstration with the 8-bit CCD, which is a sequence of gates, MOS gates, close to each other. In this case, you use 3 phases. So each bit is composed of 3 electrodes and 3 biased, and with 3 phases. And this you repeat by any bits, any times, depending on the number of bits. And this is used to transfer charge. This charge is in the well that is biased, the electrode that is biased. For instance, phase 1, you have 3 phases. Phase 1, you bias this one. this one and the next one, and so on. If there is charge available, it will be in this well. If there is no charge, no information, it's zero. But if there is, they will stay in this well, potential well. Then you apply voltage to the next electrode. The charge will be split between the two wells, and then you release this phase, and it will stay under phase 2. And this is the principle used to transfer charge. So it is charge coupled device. It's not a transistor. The number of charges that depends, if it is a sensor, optical sensor, depends on the light, but it could also be injected by the first a diode connected to this. It had applications in principle for memories and for filters, RF filters, and imagers. But it's the one that is used up to now is as the imagers. So one issue is the gap between electrodes, so that make this not ideal. And there will be some potential bump here, so that not all the charge will be transferred. So reducing efficiency. Also, you can have surface states that trap part of the charge, so that also reduce efficiency. So the first one can be solved by overlapping. So using gates that are overlapped one on the other, and the charge trapping can be reduced by using a buried layer. So then it will be not a surface CCD, but a bulk, but a buried channel. And then you have an issue that's an issue for any dynamic circuit, that is any charge that is generated in a bulk becomes leakage charge or dark current for a CCD, and that will improve, reduce quality of your image. So that's another important issue. So with that, you need to use high quality wafers and processes and or gathering techniques. So for making CCDs, we started to consider working on gathering. But for imagers, of course, the electrode cannot be a metal, but should be transparent metal electrode. Like ITO, indium tin oxide, or SiO2. This is CCD we fabricated and developed. I was also a demonstrator with overlapped two polysilicon electrodes overlapped, but making even so three phases a bit structure, and with some electronic for readout. So this was actually my part of my PhD. But for studying, I used a buried channel. So for that, you need, in order to understand better CCDs or also MOS transistors, the gated diode device is very useful to understand the physics and extract parameters. So that's what we also did using large gated control diode. And for our surprise, our reverse current was different from what was published in the literature. Because in the literature, normally the reverse current, it grows when the depletion region increases. which is expected. But in case you can reduce much the bulk generated current, the surface generation is predominant, and then the behavior is much different. So by using gathering techniques, we improved much the leakage, and because of that, the classical behavior did not follow our experiments. And that was due to our employing gathering. So gathering idea is to improve lifetime, carrier lifetime. And we use two techniques. One is high temperature oxidation, 1200. In a chlorine ambient, we use HCl, but there are other compounds you can use in order to remove metals, and this also reduces stacking faults. You can have stacking faults in your wafer, and this can be reduced. It's shown that it can be reduced at high temperature oxidation in chlorine ambient. And also we used phosphorus doping on the backside. Very high doping generate misfit dislocations in the backside of the wafer. And these defects, these misfit dislocations, are parallel to the wafer, and they are can act as gathering sites. So any impurity metals in the wafer, they are condensed or gathered at these defects. And with that, we got retention times for MOS capacitor by pulsing for over 30 minutes. You have to wait more than 30 minutes to return to equilibrium, and extracted lifetimes of a few milliseconds. And that's why we had a different reverse current behavior in the diodes. Besides CCD, we also worked on active pixel sensors, which are also imagers, used for imagers. Active pixel sensor, you use a basic diode, photodiode, and that can be done in standard CMOS. And where you have this diode biased by a reset transistor, and then it can be recharged by the light, and then you have a readout circuit here to see the voltage falling down according to the light absorbed by the photodiode. And time to time you do a restart, reset, and readings. So that's the imager works. You can also improve dynamic range of this by using an algorithmic CMOS, APS, where you have a transistor working in weak inversion. So exponential as logarithmic behavior. With that, you improve dynamic range. And if you put more transistors in series, you can even improve more the dynamic range. So we have here these 4 different number of transistors in series. When you use 4 transistors in series, the voltage range is improved. You see, having 184.5 millivolts per decade, or extrapolating for longer, the total dynamic range can be up to 126, which is much larger than for CCD. So comparing CCD and active pixel sensor, CCD is demonstrated having better quality images, better noise figures, higher sensitivity, but lower dynamic range, and higher price, higher cost. So CCDs are not non-standard process, so they have higher cost. So you have both are on the market on different products, and so it depends on what you pay. You want depends on the case. You choose one or other. And just one example here of a ultra-fast camera application. I saw this week. We have INPI as a National Research Center for Space, and there is one guy specialized in lighting, and he uses very fast cameras to study how the lights, pictures of the lightning at different stages. Brazil is known as one of the regions with the highest density of lightning in the world. So they studied this carefully. We also worked, I had a team working on silicides for a long time. Silicides is needed for CMOS and other applications. And that is aimed to reduce source and drain and gate series resistance. So you shunt your silicide on top of the source and drain and on top of the gate in order to reduce this sheet resistance and contact resistance to it. But there are requirements to limit silicon consumption. You also need to avoid, the big issue is to avoid shortening between gate and source and drain, because the metallization first happens over the spacer also, which is an insulator. And then you need to trigger the thermal treatments so that it doesn't form a silicide bridging the gate to the source and drain. So you need to design your process in order to avoid that. It needs to maintain integrity and smooth surface, low resistivity, and sheet resistance, and low film. And there was, in the 80s, people started with titanium, switch over to cobalt, and later on nickel silicides. And we followed all these three stages. We worked on these three types of silicides and had some contributions to this, to the understanding and processing. Then I would like to switch to another topic, which is integrated optoelectronics and 3.5. Optoelectronics, integrated circuits, 3.5 semiconductors, and HBTs. This is just from textbooks, where maybe some of the students didn't learn about 3.5, only silicon. The Venn diagram for 3.5, many of them, are different from silicon in terms that the Venn diagram in gallium arsenide, for instance, the wave factor is the same for holes and electrons at the minimum energies. So the transition is easier, just changing energy. One photon can do this work. But for silicon, it is known as, we call it indirect bandgap, where besides gaining a photon, it needs also have some interaction with another particle that changes its wave factor or momentum. So 3.5s are best material for optoelectronic devices, lasers, photodetectors, solar cells, and so on. And 3.5s are less efficient. You can make a photodetector, a solar cell with silicon, but the efficiency is lower. And another important factor is the lattice constant of these semiconductors. Here you have silicon, and most of them have larger lattice constant. Only a few gallium phosphide and aluminum phosphide are close. Germanium is larger. Gallium arsenide is almost 4%, 5% mismatch. So it is not easy to grow this material on silicon. However, we have silicon germanium, commonly a mixture of germanium and silicon on silicon, but depending on that is also always under stress. If it is taken off, it relaxes the stress, but produces defects. So there are tricks you can play with. But for C5s, there are more options to grow without. For instance, you can grow aluminum arsenide or a ternary compound, aluminum gallium arsenide on top of gallium arsenide. You can grow indium phosphide on top of this ternary material, a mixture of gallium arsenide and indium arsenide called InGaAs, with the same lattice constant but different band gap. So that's important for making optoelectronic devices, but also HBTs. Then we need to consider mobilities. Mobilities in general trend is lower band gap, higher mobility. So germanium and but also got most of the C5s have higher electron mobility than silicon. And for holes, germanium is the champion, but they are also indirect type of band gap. So this is important also to consider when designing optoelectronics and HBTs. For HBTs, we need to have an emitter that has larger band gap than the base in order to have high gain, even with high doping of the base. And that's possible because of the offset of the band gap. So there is some band offset in the valence, so that it makes it less probable to emit holes from the base to the emitter. There is a little offset here in the emitter also, but you can remove this by graduating the composition, the transition from the emitter, our gas to gallium arsenide, removing gradually the aluminum content, reducing. So there are examples of all gas on gas, InGaP on gas, silicon on silicon germanium. They all result in HBT with high gain, even with a high base doping, which is important to reduce base resistance and crowding, emitter crowding. So, and you have also they provide high power density and efficiency, and with low 1/f noise, characteristic of bipolar, and high FT and Fmax. So that are characteristics of HBTs. On the C5, normally they use Mesa type of structure to contact subcollector and the base and emitter. With that, you can also integrate on the same material high-speed electronics and optoelectronics, so the laser, photodetectors, modulators, and others. This is one example where we integrated pin photodiode using the base and the collector, lightly doped, and the subcollector. There's a pin with bipolar HBTs. So but we also, in other design, we replace this simpler processes with MSM, metal semiconductor, metal photodiodes. So we had some contribution in this field. Also, we fabricated a laser on the same substrate as the HBTs by selective removing the after HBTs, removing after HBTs growth, removing regions to do a regrowth in only local growth, selective growth for the laser. So you can do different kinds of integration. And to finish, I just wanted to mention something about structured methodology for IC design. I did also work on some IC design, and I managed some programs for universities for prototyping, encouraging prototyping ASICs. But for that, we need to consider I am from the 70s. I started in the 70s, and in that time, there were not only specialized. Most of the people worked on semiconductors, doing processing and design. But in 1980, Lynn Conway, she was fired from IBM, and she was a specialist in digital systems and went to California and was interested in working in IC design without having a background of semiconductors. And with that, she developed a structured way of methodology for IC design. And they came out with this basic course she gave and wrote this book together with Carving Meat. And this was a change in the culture of semiconductor, with people now being more specialized in design and more specialized in processing, fabrication, and devices. And that was a great thing for the semiconductors. More people were able to design integrated circuits. However, not all of the designer has the background, and you need some background. To being a good IC designer, I always say it's important, especially the back-end designer, the one that draws the final layout, and he needs, but also other stages, you need always to know device physics, compact models. And he encounters many design rules. It's good to understand them. So, and they come from knowing the technology, fabrication processes. For instance, antenna effect has to do with plasma etching. The plasma etching can charge a line of metal. And if this metal is connected, is long, and is connected to a gate, it can charge and destroy the gate dielectric. So those are all effects that are known from the technology, and it's good to know the reason and what to do with that. Also, electromigration, why limiting the width of your metal, reliability, radiation effects. How can I make design that's hard against radiation? Okay. Question of metal slotting. Why is that? It's because of stress in metal lines that are that do not have these holes, these slotting holes. Dummy filling. Why do I need dummy filling? And in some cases, if you don't advise the fabrication, the fab, they put themselves the dummy filling, and that can destroy your RF circuiting. That happened with us one time. So the student didn't inform, and then the fab added dummy filling of metal, and that affected his RF design. Latch up is an important issue. We need to consider to know electrostatic discharges and the PET design to protect your design, die sealing ring, scribe laying areas. When can I use? I can use them for test structures many times. Considerations of yield and corners. I do need to do corner simulation because there are some spread of the parameters between some range. You can have DRC errors, LVS errors. You need to identify. In some cases, you can even waive these errors, but for that you need to know what you are doing. So it's important you know more about technology and to finalize your design. Also about mask making, dark and clear fields, mask grade. You have options of full mask or multi-level mask cost issues. So there are many electron device issues, which also are important for circuit designers. So although after this new culture, you have people more specialized in design and others in technology, it is important that a good designer has also some knowledge of electron device issues. And I think with that, I would like to summarize with some statements. So we have 74 years of transistors that brought tremendous progress to the technology and society in general. My 50 years of experience allowed me to follow different technologies and evolutions, and some I described in this presentation. I did more activities than that, but and semiconductor is a multidisciplinary and fascinating area, and that has gone through this enormous evolution. And we have seen great breakthroughs, but also many small contributions. Some of these allowed this tremendous progress. And also third world countries made relevant inventions and contributions. Not only Silicon Valley did semiconductors, although they did great and very honorable work, which we all appreciate. And with that, I think I thank you for your attention and would like to hear questions and comments.
Thank you. Thank you very much, Professor Swart, for taking us down this 50 years journey of yours. And I must appreciate, along with the attendees, that they must have been immensely benefited by some of the generic topics which you have covered, and the way with ease that you have explained, this is also, motivational and a true guiding force for all the young teachers, researchers who are going to venture out in the area of teaching and research in the area of microelectronics. Well, there are a few questions which have been shared by the attendees through the chat. I'm going to share my screen now. I hope it is visible to you.
Yes, I see.
Yeah.
So is Brazil still developing ICs with high density or micron dimension? And if so, what are the application of these ICs? Most of the work in the industry here is mainly in IC design using foundries, foundry service. There is one local foundry that went through some trouble, but will be put again on trail, and that is for basic CMOS and probably with MEMS or sensors. But I think we will not compete with the submicron development. Just for research, yes, at universities, there are many groups working on advanced devices, modeling, and some fabrications for studying this, but not for fabrication. For fabrication, there is one company doing power devices. As I told, IC design houses. And we have 5 companies doing advanced packaging of memories. And that seems to be one of the few places outside Far Asia. So all packaging happens mainly in the Far East. And in Brazil, we have 5 fabs doing mainly memories, but also some others, system in package. With stacked memories, so even 18 levels of memories. So they do advanced packaging, and that's maybe a good opportunity for Brazil being a hub for packaging. But I don't see Brazil being having a fab on an advanced leading edge CMOS. CCD, a charge coupled device. So it's a MOS device, is not a transistor, where you have wells, potential wells, produced by these MOS gates. And these wells can be filled with electrons generated by light, for instance, for an imager. So the charges generated depend on the light coming in. And so you can have a picture. And then these charges are driving out sequentially. The bits, the pixels are driving out to the end through a sequence of pulses. So, and it has some advantages compared. So we have cameras everywhere, right? For all kinds of applications. And CCD is a special one. It is more expensive than the APS, but there are applications for both. Field factor in active pixel sensor is the area, the percentage of the area of the pixel used by the sensor itself. You have an active pixels, you need some electronics around it. The precharge, the readout. So the field factor is what's the percentage of the area of the pixel occupied by the sensor itself. So the higher the field factor, the better. or was this for APS? I think so. Yeah. Ik ben luisteraarsfilm. Luisteraarsfilm was this with silicon germanium. When I thought about silicon germanium, I don't remember why this. So for HBTs, if you use HBTs on silicon integrated circuit, the base is silicon germanium, and this will be under stress because the lattice factor is somewhat larger than silicon. But if it is thin, it stays under stress compatible with silicon. I think this was the question. Direct bandgap are having high direct bandgap, high bandgap in EV. Not always. Direct bandgap depends which one. Gallium arsenide has a higher bandgap than silicon, but in us, antimonides, they have very small bandgap. So not all C5 have larger bandgap, but many of them have. Yeah. So indium phosphide, gallium arsenide, many of them have higher bandgap in EV. Yeah. You will need higher work to be done to eject light. For solar cell, for instance. No, for the cell receives. For a laser, ejection of light depends on the light you want. So what color do you want? For a laser, there are some applications for a laser, and that depends on the light. They also choose lights for lasers according to the absorption in the optical wires, optical guides, the lines, optical lines. So where you have less absorption, that is the color you choose. For LED, you need the 3 colors. So that's including larger bandgap. So the for generate is for light, for LEDs and for lasers. But for detector, depends also what light you want to detect. But you can detect easier because you only need absorb the electron, yeah, the photon. Gallium nitride. There's a very large bandgap, like silicon carbide, and they are aimed for high voltage and high temperature applications. So that's the reason why the applications that need higher temperatures, like for instance in the automobiles or any other applications with higher temperature and high voltage, then they look to gallium nitride and silicon carbide. They are competing. Both technologies are being used and considered, being worked on. The scaling of silicon, silicon is a surface. You can scale both. In 3.5 US, you also have amps, so or other FET devices in 3.5. And normally they used, there was a competition between scaling silicon and 3.5, because 3.5 always had higher mobility. So you could make faster transistors in 3.5. However, then the technology developed more on silicon, and then they competed out with the 3.5. But in principle, you can scale also 3.5. 3.5 has always been the material of the future. And some people considered integrating 3.5, yes, on silicon, using integration of 3.5 on silicon and germanium on silicon because of higher mobility. But you can scale all of them, where polarization bandgap engineering is involved. Polarization, you mean optical polarization. So for optical, yes, bandgap engineering, but also silicon, you use bandgap engineering when you use silicon on silicon germanium, HBTs or FETs on the silicon germanium. So this also applies to both silicon and 3.5s. The gladding is like optical fiber that has a lower band index. So depends of the composition more. And they used it as I don't remember exactly now, but cladding is guiding electronic ICs. So you need to guide your light in the laser, and so it doesn't be lost in the substrate. Explain how the pixel sensors is detecting. It's a photodiode, polarized, and the light generates pairs of electron and holes. And electrons are attracted to the positive terminal, and then they separated by the diode. So they are generated by light, pair electrons, hole pairs, and then they are separated by the electric field of the polarized diode. I don't know if I replied well the questions.
No, I think I'm just checking out the chat section. I cannot see any more questions which are there. And thank you very much, Professor Swart, for sparing your valuable time and taking up all possible questions.
Yeah, it was a great pleasure participating to this series organized by your society.
Thank you.
I wish success for the next presentation.
Thank you. Thank you very much, sir. Thank you. Thank you.
Okay. Thank you. Goodbye.
Okay. Bye-bye. Bye.
Bye-bye.